Good day to everyone. So in the last video, we have discussed about the center of pressure of different geometrical objects. And in particular, we have discussed about the finding the center of pressure of the rectangle as well as the triangles of triangles. So in this video, we are going to discuss about the equilibrium. Suppose if you throw any object into the liquid, then it will be a float or a sink based on the weight of the material and the density of the liquid. So what happened? Suppose when the body is actually floating, and how this equilibrium is affected by the perturbation. That is what we are going to see in this video. Suppose if you consider a body which is actually immersed wholly or partially in a liquid, which is actually suspended by the two different forces. One is the weight, which is actually acting downwards, and the equally opposite upthrust force, which is actually acting on the opposite direction. So this downward force is actually the vertical force, the weight which is actually vertically acting downwards through its center of gravity. Suppose if I consider there is some point that is maybe taken as a G, that is the center of point of the corresponding object, and the weight is actually acting from this along this line, and we have another force, that is the upthrust W prime, acting vertically upwards at its center of point, the center of buoyancy. That means due to this Archimedes principle. Suppose if we consider the another point which is actually lying on the same vertical plane, let us take this B. Then the buoyancy force of W prime is actually acting vertically upwards in the same line from at its center of buoyancy B. So the points center of gravity point G and the buoyancy force P is actually the two points in which the two forces W and W prime is applied respectively, which are actually coinciding with the line with which are actually vertically coincide with in line with each other, which is called the center line of the corresponding object, which we have considered. So the floating or a sinking or or being still of this object is actually depending upon the forces W and W prime, which is based on the W which is equal to W prime, or W which is greater than W prime, or W which is less than W prime. So these are the three cases. Based on these three cases, whether this object is actually float or sink or remains the same. Suppose if I first consider the W is actually greater than W prime, that means the weight of the object is actually greater than the buoyancy force, then obviously the object will sink sinks further down, which is actually displacing more and more water above the liquid, and thereby increasing the upthrust until the two forces actually equating each other, and one if it is reached, then the object will remains in the same position when W is equal to W prime. So that point is actually called as the equilibrium point. And if W is equal to W prime, obviously the two forces on the object is actually equal and opposite to each other, so that they neutralize each other, and the body remains floating in the liquid at the same position. Okay. Finally, if you consider this W is actually less than W prime, then the body is actually rising upwards, because this buoyancy force is actually greater than the own weight of the object which we have considered. So the body is actually rises up, so that the lesser volume of it actually is under the liquid. That is, it displaces a very small amount of liquid, and the upthrust force is actually upthrust force on it is very less. Therefore, if you continue, if you are actually concentrating of the equilibrium of the floating bodies, then the two different conditions are actually necessary for the equilibrium for floating of the body. One is its weight must be equal to the weight of the displaced liquid, according to the Pythagoras theorem, and then the center of gravity of the body and the center of the buoyancy force is actually keep on the same vertical line. Okay, so these are the two important conditions for the equilibrium of the floating bodies. Okay, so now we are going to see how, suppose if any body is actually floating on the liquid, and how this stability of the equilibrium is actually affected once if you are giving any perturbation. Suppose if you considering the same body which we considered earlier, and if the floating body is actually tilted with a little on one side of the one side or other side of the from the angle of theta, and the angle of the theta is very small, then the weight of the displaced liquid or the upthrust on it remains the same. Then since the shape of the shape of the liquid which is actually removed is actually different, because it is actually tilted with this some angle theta. So whatever the theta which we have displaced in the one direction, that means the right hand side will be changed in the same thing, direction of the right hand side also. Therefore, this the total weight of this water which is actually displaced in this direction, this right hand side is actually equalized by the left hand side. However, the shape of this shape of the water which is actually displaced is actually different. Therefore, the center of buoyancy force actually shifts a little, which is, let us say this B is the original position, and if due to the shift we have a due to this small perturbation of this angle theta, we have a small shift of this buoyancy force. That means from the object from here to here, let us take this point as B prime, so that the vertical line which is actually drawn upwards from this point B prime, which is actually meeting the object at some point. Let us take this point as M. Then this point M is called as the metacenter of the body, and so the distance between this point M to the center of gravity G is actually known as the height H, that is called the metacentric height. So this height H is equal to the metacentric height. Metacentric height. The distance between this point where this the new buoyancy force acting on this body is actually, if you plot a direct vertical line from this point B prime, which is actually meeting the object, the vertical line of the object which is at some point, that is called the metacentric point or metacentric of the body, and the distance between this metacentric and the gravitation, the center of gravitation, is known as the metacentric height. Okay. So based on the position of this metacentric point M, which is actually coincides with G, or which is lies above or below the G, based on this the shifted position of the center of gravity G prime of the body. So based on this dependence upon the shift shape of the body and the equilibrium of the body can be determined, so that suppose if it is lies with this same in the the same line, or it is actually above or below the center of gravity. Based on this, you can classify the stability as neutrally stable, or a completely stable or unstable equilibrium, based on this the position of the metacentric point M. Suppose this floating object is in a circular sphere or a circular object, then the tilt on this way or any other way which will not actually change the center of gravity, and also the shape of the displaced liquid will also not change. Therefore, this metacentric point will always coincide with the center of gravity, so that it is actually this kind of situation is called the neutrally stable. That means if G, which is exactly equal to the M, then the object is actually neutrally stable. And one of the example is the circular object which is actually tilted into the water. And suppose if you consider the rectangular body like this, and which is actually floating in this manner, then the floating so this metacentric is actually lies above the G, the center of gravity, so that at this position, the tilted position, the couple actually produced in the which is actually formed by this W and W prime. So you can see this, the center of gravity, the W is actually acting in the downwards in this point. However, the buoyancy force actually slightly moved from the original position. So therefore, the upward force W prime, that means the buoyancy force, is actually acting upwards in the different position. And both these forces are equal, but however in opposite directions. Therefore, there is a couple will be produced. So this couple is actually trying to rotate the body back to the original position. so that this once the metacentric point is above this gravitational the center of gravity, then the corresponding case is actually known as the stable one, because this couple is actually trying to keep the object in the original position. That means it actually try to regulate this the perturbation theta, so that the restoring force, which is actually the restoring couple actually acting on this, is equal to this W into G prime of M. G prime is the newly shifted center of gravity, so which is W into G prime into M into sin theta, so which is the restoring couple. The restoring couple. So this restoring couple is also known as the righting moment. The righting moment, because this righting moment is actually tends to bring the body in the original position, so that if there's any rectangular object is actually being in this position and the metacentric point is actually above this center of gravity, then this point, and if you give any perturbation, then this perturbation will be died out, and it, finally this object will come to the original position of the same position what we have seen in the other case. Okay. Okay. So the another case is what happen if the metacentric point is actually below this G. For example, if you consider another example, so in case of if you consider the same rectangular body which is actually floating in this manner, is shown in this figure, so that the metacentric point is actually acting, lying below the center of gravity G. So this is the original position. The dashed line is the original position of the rectangular body, but there is a small shift in this theta. So therefore, there is a small different deviation in the center of gravity as well as the buoyancy force. So that the weight is actually acting downwards and in this direction. However, the buoyancy force actually from the new position of the B prime, which is actually acting upwards, which is actually in the W prime, which is actually meeting the point center of gravity at this point. It is actually known as the metacentric point. Therefore, here also we have the couple which is produced due to this W and W prime, which is actually tends to rotate the body further in the same direction in which it has been tilted already. For example, if it is actually tilted in this direction, so that the couple is actually trying to rotate the same, or rotate the object in the same direction, so that it has been tilted in the object will not coming to the same original position. However, but due to this rotation, this object is actually coming to this position, so this original position, which will not coming to this the position which is going here. So that when the metacentric point is lies below the center of gravity, then if you give the perturbation, then the object is in the unstable equilibrium point. Okay, so all these three cases can be explained with the example of the simple pendulum. For example, if you take any simple pendulum with mass, weight is actually acting downward, and which is actually another end is fixed on the other value, so that the weight is actually acting downwards. So if there is no equilibrium, then there is no perturbation, then this the center of gravity is actually keeping in the same position. Suppose if you give any perturbation, small perturbation theta from this point, then it is actually oscillating in this direction, and the oscillation will be die out due to this damping and coming to the same position, that is the equilibrium point. Or if you consider the same simple pendulum but in the upward direction, for example, if I take this bob and directly upwards from the wall, so this is an unstable point. Suppose if I give any perturbation from in this direction or in this direction, suppose if I give the direction in the right hand side, then the bob is actually moving in this direction and coming to this rest position, and while oscillating, and this damping will be died out and coming to the same rest position. So this point, that means the opposite direction of this simple pendulum is called the unstable point, and this point is actually the neutrally stable point. Okay. So in a similar way, suppose if you consider the rectangle object, and if you give any object, any deviation theta here, so that this is actually making the oscillatory motion, and due to this density of this into the and the viscosity of this liquid, and this the damping will be, the oscillations will be died out, and eventually it is coming to the rest position. Similarly, in this direction also, if you having this rectangle bar in this position, and if you give any perturbation, then again it is moving to the same position like this. After making the damping actually, the oscillations will be damped out. Okay. So now let us discuss the same problem in a little more detail with the in particular reference with the floating vessel or floating ship. So let us consider this is the bottom of the ship, which is actually lies in the water, and this G is the center of gravity, and B is the buoyant force acting on this, which is actually lying on the same vertical line. So that at the equilibrium point, then the weight is actually the weight of the ship will be equivalent by the buoyant force. That means the liquid actually replaced by the weight of the ship. So the center of gravity as well as the buoyant force will actually lie on the same vertical line. So that there is a symmetry between the opposite, the both left and right direction along this vertical line. So if, however, suppose if the ship is actually rolling or tilted in the one direction with an angle of theta, as like in this case, suppose we consider this is a ship, and if it is actually tilted with some angle theta, therefore the plane of the symmetry is actually no longer vertical, and although this rolling and tilting does not alter its center of gravity with respect to the ship, but however the buoyant force is actually shifted towards some distance, which is actually giving rise to the righting moment, which is actually given here. So that this righting moment is actually equal to this W G prime of m into sine theta. So this, since the G prime m, the distance is actually taken as the h, we can write this by righting moment as the W times of h into sine theta, where the h is the distance from this metacentric point to the center of gravity. So suppose if the theta is very small, then I can write this expression as W times of h into theta. That means the righting moment. So that if you consider this expression, it is very clear that if the height is actually larger, the height is very greater, then the metacentric height of the ship or any other floating object is greater than the stability of its equilibrium. So based on this the expression, the ships are actually designed accordingly to be just withstanding for the rolling and tilting. So this righting moment of WH times of theta is acting on the ship when it is tilted through a small angle theta, results in an oscillation. As I told you that due to it actually producing the oscillations, and this are rolling. So and this oscillations can be the time period of the oscillations can be given as T is equal to 2 pi times of root of I divided by m, where this I is the rigidity of the ship, the moment of inertia of the ship, as well as the m is the turning moment of the ship. So that which is actually resembling which is actually resembling the time period of the simple harmonic motion. So the T is equal to 2 pi square root of I divided by m, which actually determine the time period of the oscillations of this ship. So this turning moment is for the unit deflection is equal to the W times of h, because if you take this unit deflection theta is equal to 1, then the turning moment is equal to the W times of h. So that I can just substituting this W times of h into this turning moment, then I can get time period as 2 pi T is equal to 2 pi times of I divided by W into h. So that you can see this from this equation, the time period is actually inversely proportional to the square root of the metacentric height h. Therefore, a ship with the small high metacentric height is actually therefore very less liable to the rolling. So for this reason, the large ships are actually designed to have a very comparatively a small metacentric height of just exactly very few meters height for making the small displacements. So which obviously makes them much more stable than the other cases. So at the same time, however, to avoid the danger of the ship turning over, the metacentric height is actually also adjusted or increased to make it to withstand for the large deflections also. So now we're looking into the theory of how to determine this metacentric height using any small experiment. So if you consider the same experiment, that means you can consider the ship with this is the center of position, and if there is a small deviation through an angle theta, then which is which is actually making the wedge shaped portion of the ship, which is actually immersed in the right hand side of this and an equivalent wedge shaped portion is actually raised on the above the water and the left hand side, so that we consider the wedge shaped position. So this wedge shaped position, and this portion is actually divided into a number of small elements which is actually vertical to the perpendicular to the water surface. So and you can have an infinite number of such vertical portions, and if you consider the small portion which is having the height of h, which is distance from this point origin O, let us take this distance is actually taken as a h x. So the distance is the distance from this O to h is O to this point is taken as a x. Then the tan theta of this can be written as tan theta, which is equal to written as h divided by x, or this height can be written as height can be determined from this equal to x times of tan theta. And if the theta is very small, then I can just replace this tan theta into theta, so that I can write h is equal to x times of theta. And the area of this small portion is actually considered as dA. The small portion which I consider the area having this dA, then I can find out the volume of the prism as, so the volume of the portion is this height into this the small area, so that I can write as x into theta into dA. So that is the volume of the portion which we have considered, so that I can easily find out the mass of this from this volume. I can find out the mass just by taking the density of the water which is displaced by this portion, so that I can take this rho is the density of the water, and I can write the mass of the water which is displaced by this vertical, the small wedge type of geometry, the shape portion. Then I can write the mass as x times of theta into dA multiplied by the rho. So that is the mass of the displaced water, and we can the rho is the density of the liquid which we have considered. So once you know the mass, then we can easily find out the weight of the prism or a mass of the water which is displaced, with the T actually given as upthrust of the portion, which is equal to x theta dA times of rho into g. So that is actually the upthrust of the portion, so that I can easily find out the momentum along with with respect to this point O. I can write moment about the origin O, which can be written as x theta dA into rho g multiplied by the another the distance x, so that I can write it as x squared theta into dA rho times of g. So similarly, if you consider the same equal wedge shaped portion in the left hand side, we find that there is a loss of upthrust due to this rising out of the water, so that the moment with respect to the origin O, which is obviously equal to this expression which we have considered for both left hand side as well as right hand side. Therefore, there is a moment acting on this couple. The couple acting on this ship is actually equal to the due to the displacement is can be given by just integrating this equation for the whole range of from 0 to some value, so that I can just take this the integration of rho g times of theta x squared into dA. I just rewriting this equation. Just I can take the constants outside, rho g times of theta integration of x squared into dA, and we already know that the integration of x squared into GA is actually known as the geometrical moment of inertia, so that I can replace this integration of x squared dA as ak squared, where this k is the radius of gyration of the given axis. So this displacement theta of the ship is actually being very small, then the volume of the water displaced remains unaffected. Suppose if the theta is very small, however, the upthrust which we have calculated, that is rho times of g into v, the volume, which is actually due to the displaced water, which actually acts through the new center of buoyancy force due to this slipping. For example, if the rest position the g is actually here, the b is here, due to this tilting there is a small deviation in this b prime, so that this upthrust force is actually acting from this newly displaced buoyancy force, with therefore this ship is actually experiencing the couple which is equal to the equal to this rho times of gv into bm into sine theta. So the bm is nothing but the distance between the buoyancy force as well as the metacentric object, the metacentric point. So that I can write this. Suppose if the theta is very small, then I can write this equation as rho g times of v into bm into theta. So this is another couple acting on the ship. Therefore, I can just equate these two couples which we have considered earlier and this one. So I can just equate these two. So rho g v into theta, sorry, bm into theta, which is equal to x squared theta into x squared g theta into ak squared. Sorry, this is rho times of g into theta ak squared, so that I can cancel out all the constants in both the direction, both the left hand side as well as right hand side, so that the final value is bm into v, which is equal to the ak squared, or I can write the bm, that means the distance, which is equal to ak squared divided by v. So this bm is nothing but the metacentric height. Suppose if I take this as metacentric height as h, then which is equal to ak squared divided by v. So the ak squared is nothing but the geometrical moment of inertia of the ship which we have considered, and v is the volume of the water which is actually displaced from the displaced due to the angle displacement of angle theta. So this is not actually the metacentric height. This is actually the height of this from this height from the rest position. So actually we require to calculate this b prime into so the bm is actually the total height of this. So but we require to calculate this g prime m. So the g prime m can be written as the b prime bm minus this g prime m, so that I can write this expression as, so this metacentric height h can be written as this g prime m minus, sorry, g prime m, which is equal to bm minus b g prime. So that is a bm which we already calculated as ak square divided by v minus b g prime. So therefore, using this expression, we can find out we can determine the metacentric height using this formula. Okay. So that's all for today's in the today's class. And if you have and we can see the remaining portions in the next class. Okay. Thank you.